Okay, last time I was reading and I stopped at 1.13, so we'll pick up there. And that's the definition of addition in f to the n. It's defined by adding the corresponding coordinates. So you just take like the x1 and add it to the y1, x2 added to the y2, like that. Often the mathematics of f to the n becomes cleaner if we use a single letter to denote a list of n numbers, without explicitly writing the coordinates. For example, the next result is stated with x and y in f to the n, even though the proof requires the more cumbersome notation of x1 through x to the n and y1 through y to the n. Commutativity of addition in f to the n. If xy is in f to the n, then x plus y equals y plus x. Suppose x equals x1 through xn in f to the n, and y equals y1 through y sub n in f to the n. Then x plus y is the x list plus the y list. So you add them coordinate-wise. Because x and y are in a field, they're commutative, so they can be written as, instead of x plus y, y plus x, and in coordinates, and then they can break it up from the rule of the way you add them, and that gives you y plus x. So that proves commutativity in general for the list, where the second and fourth equalities above, according to him, hold because of the definitions of addition in f to the n, and the third equality holds because of the usual commutativity of addition in f. The symbol, the box, means end of proof. I know that as the Helmholtz symbol, to be honest. I think Helmholtz started using the box before this, or popularized it. If a single letter is used to denote an element of f to the n, then the same letter with appropriate subscripts is often used when coordinates must be displayed. For example, if x in f to the n, then letting x equal the list x1 through xn is good notation, as shown in the proof above. Even better, work with just x and avoid explicit coordinates when possible. Notation 0. Let 0 denote the list of length n whose coordinates are all 0. Here we are using the symbol 0 in two different ways. On the left side of the equation above, the symbol 0 denotes a list of length n, which is an element of f to the n, whereas on the right side, each 0 denotes a number. This potentially confusing practice actually causes no problems, because the context should always make clear which 0 is intended. Context determines which 0 is intended. Consider the statement that 0 is an additive identity for f to the n. X plus 0 equals x for all x in f to the n. Here the 0 above is the list defined in 1.15, not the number 0, because we have not defined the sum of an element of f to the n, namely x, and the number 0. A picture can aid our intuition. We'll draw pictures in R² because we can sketch this space on two-dimensional surfaces, such as paper and computer screens. A typical element of R² is a point v equals a comma b. Sometimes we think of v not as a point, but as an arrow starting at the origin and ending at a comma b, as shown here. When we think of an element of R² as an arrow, we refer to it as a vector. When we think of vectors in R squared as arrows, we can move an arrow parallel to itself, not changing its length or direction, and still think of it as the same vector. With that viewpoint, you will often gain better understanding by dispensing with the coordinate axes and the explicit coordinates and just thinking of the vector, as shown in the figure here. The two arrows shown here have the same length and same direction, so we think of them as the same vector. You should know that mathematical models of the economy can have thousands of variables like x1 through x sub 5,000, which means that we must work in R to the 5,000. Such a space cannot be dealt with geometrically. However, the algebraic approach works well. Thus, our subject is called linear algebra. Whenever we use pictures in R squared, or use the somewhat vague language of points and vectors, remember that these are just aids to our understanding, not substitutes for the actual mathematics that we will develop. Although we cannot draw good pictures in high-dimensional spaces, the elements of these spaces are as rigorously defined as elements of R squared. For example, 2, negative 3, 17, pi, square root of 2 is an element of R to the 5th, and we may casually refer to it as a point in R to the 5th, or a vector in R5, without worrying about whether the geometry of R5 has any physical meaning. Recall that we define the sum of two elements of f to the n to be the element of f to the n obtained by adding corresponding coordinates. See 1.13. As we will now see, addition has a simple geometric interpretation in the special case of R squared. Suppose we have two vectors u and v in R squared that we want to add. Move the vector v parallel to itself so that its initial point coincides with the endpoint of the vector u. As shown here, the sum u plus v then equals the vector whose initial point equals the initial point of u and whose endpoint equals the endpoint of the vector v, as shown here. In the next definition, the zero on the right side of the displayed equation is the list 0 in f to the n. The additive inverse in f to the n of negative x. For x in f to the n, the additive inverse of x, denoted by negative x, is the vector negative x in f to the n, such that x plus negative x equals 0. Thus, if x equals x1 ... x sub n, negative x must be negative x1, comma, ... comma, negative x sub n. The additive inverse of a vector in R squared is the vector with the same length but pointing in the opposite direction. The figure here illustrates this way of thinking about the additive inverse in R squared. As you can see, the vector labeled negative x has the same length as the vector labeled x, but points in the opposite direction. Having dealt with addition in f to the n, we now turn to multiplication. We could define the multiplication in f to the n in a similar fashion, starting with two elements of f to the n and getting another element of f to the n by multiplying corresponding coordinates. Experience shows that this definition is not useful for our purposes. Another type of multiplication, called scalar multiplication, will be central to our subject. Getting another element by multiplying corresponding coordinates. Specifically, we need to define what it means to multiply an element of f to the n by an element of f. The product of a number lambda and a vector in f to the n is commuted by multiplying each coordinate of the vector by lambda. So lambda times x1 through xn is lambda x1 dot 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 lambda x sub n. Here lambda is an element of the field f, and x1 through xn is an element of f to the n. The blurb here says scalar multiplication in f to the n multiplies together a scalar and a vector, getting a vector. In contrast, the dot product in r squared or r cubed multiplies together two vectors and gets a scalar. Generalizations of the dot product will become important in Chapter 6. Okay, back to the text. Scalar multiplication has a nice geometric interpretation in r squared. If lambda is greater than 0 and x is an element of r squared, then lambda x is the vector that points in the same direction as x, and whose length is lambda times the length of x. In other words, to get lambda x, we shrink or stretch x by a factor of lambda, depending on whether lambda is less than 1 or greater than 1. If lambda is less than 0 and x is an element of r squared, then lambda x is the vector that points in the direction opposite to that of x, and whose length, absolute value of lambda, times the length of x as shown here. So half x is like half the length. Negative 3/2 x is flipped around and a little bit bigger than x. Digression on fields. A field is a set containing at least two distinct elements called 0 and 1, along with operations of addition and multiplication satisfying all properties listed in 1.3. What was 1.3? Oh yeah, it was this, which I said was like a field. All right, thus R and C are fields, as is the set of rational numbers along with the usual operations of addition and multiplication. Another example of a field is the set of numbers just 0 and 1 with the usual operations of addition and multiplication, except that 1 plus 1 is defined to equal 0. So that's addition, mod 2. In this book, we will not deal with fields other than the real numbers and the complex numbers, R and C. However, many of the definitions, theorems, and proofs in linear algebra that work for the fields R and C also work without change for arbitrary fields, if you prefer to do so throughout much of this book, except for chapters 6 and 7, which deal with inner product spaces. You can think of F as denoting an arbitrary field instead of R or C. For results, except in the inner product chapters, that have as a hypothesis that F is C, you can probably replace that hypothesis with the hypothesis that F is an algebraically closed field, which means that every non-constant polynomial with coefficients in F has a 0. A few results, such as exercise 13 in section 1c, require the hypothesis on F that 1 plus 1 is not equal to 0. Okay, and we already showed exercises 1 through 7. So we'll pick up with either the rest of the exercises here, or the reading the next section, or both. Thank you for listening.